What if your phone network could do more than just send messages and stream videos? What if it could actually sense the world around it, detecting drones, helping cars see around corners, or guiding robots in a factory, all without needing extra sensors? That's the incredible promise of a technology called Integrated Sensing and Communications, or ISAC. In simple terms, ISAC merges the communication job of mobile networks with the ability to sense things. It uses the exact same signals, hardware, and infrastructure that already carry our data, but adds a powerful new trick: the ability to detect, locate, and track objects in the environment, even if they aren't connected to the network. In this video, we're going to break down what ISAC is, how it works, the amazing applications it could unlock, the technical hurdles we need to overcome, and the serious privacy questions it raises. Let's dive in. So, what exactly is ISAC? You might also hear it called JCS, which stands for Joint Communication and Sensing. The core idea is to reuse our existing mobile networks, the base stations, the radio spectrum, the antennas, to not only transmit data but also to sense the physical world. Think of it like turning every cell tower into a kind of radar field. This sensing isn't just about knowing something is there. It can include detecting an object's location, its size and shape, its speed, and the direction it's moving. And this could work in all sorts of environments: in the air, tracking drones, on our roads, spotting pedestrians and vehicles, or inside factories, guiding autonomous robots. This isn't just a futuristic fantasy. ISAC is already making its way into the official standards that govern our mobile networks. The 3GPP, which is the global body behind mobile standards like 4G and 5G, is already studying ISAC for its upcoming Release 19, laying out the first use cases and requirements. Meanwhile, another major group, ETSI, has launched its own industry group for ISAC to coordinate the groundwork for what will eventually become a key feature of 6G. Alright, that's the theory. But what could ISAC actually do? Let's look at some real-world examples. First, drone detection and traffic management. Mobile networks could use ISAC to spot drones flying in restricted airspace, like near airports or over critical infrastructure. It could also help coordinate swarms of delivery drones, ensuring they navigate safely and avoid collisions in busy city skies. Next, automotive and transportation. Modern cars are already packed with sensors like radar and LiDAR, but they can only see what's directly in their line of sight. ISAC offers a god's eye view from cell towers, which are positioned higher up. This could allow a network to detect a pedestrian stepping out from behind a parked bus and warn an approaching autonomous car before its own sensors can see the danger. The same goes for railways, where ISAC could detect animals or obstacles on the tracks far ahead of an approaching train. Then there's the world of industry and logistics. In smart factories and warehouses, ISAC can be a game changer for safety and efficiency. It can help autonomous robots and human workers avoid collisions, create real-time maps of the factory floor, and even track inventory without needing a tag on every single box. Since many factories are already deploying private 5G networks, this is a perfect environment for early ISAC adoption. Perhaps one of the most clever uses is for the network to optimize itself. High-frequency 5G signals, like millimeter wave, require a clear line of sight to work best. If a truck parks and blocks that signal, your connection could drop. With ISAC, the network could sense the truck arriving, predict the blockage, and proactively switch you to a different signal beam or base station without you ever noticing. It's a network that's aware of its physical surroundings. Finally, think about immersive experiences. ISAC could help build hyper-realistic digital twins, or virtual copies, of our physical world. Augmented reality glasses could use this sensing data to make virtual objects interact seamlessly with real-world obstacles, creating a truly blended reality. So, how does this all work technically? Well, ISAC isn't a single, one-size-fits-all technology. It has different levels of integration, each with its own challenges. The most basic level is just sharing the same tower for both communication and sensing equipment. But the real magic happens with deeper integration, like sharing the same radio frequencies, the same antennas, and even the same signal waveform. This means the very same radio waves that carry your video stream are also bouncing off objects and returning to the tower to be analyzed, just like radar. The choice of frequency band is crucial. Lower frequencies, like those used for 4G, offer wide coverage but low resolution sensing. They're good for detecting large objects over long distances. Higher frequencies, like millimeter wave, provide incredible detail enough to distinguish a person from a lamppost or measure speed with precision, but they have a shorter range and are easily blocked. The signals themselves need to be smart. Technologies like OFDM, which is the backbone of 5G, are great candidates because they can be adapted for both communication and sensing. Engineers are designing clever signal processing techniques to extract information about distance, speed, and angle from the faint echoes that return to the base station. The network topology also matters. A monostatic setup, where one tower both sends and receives the signal, is simplest. But a multistatic setup, where multiple towers work together, can pinpoint an object's location with far greater accuracy, much like how our towers help us locate a sound. Of course, this requires incredibly precise synchronization between all the towers, down to the nanosecond. But with all this sensing power comes a huge responsibility. The privacy implications of ISAC are profound and need to be addressed carefully. Because ISAC senses passive objects, it can detect things that aren't connected to the network, and that includes people. A person walking down the street hasn't consented to being tracked by a mobile network. This raises critical questions. What data is being collected? How is it being used? And who owns it? Regulating consent is a major hurdle. If the sensing isn't tied to a specific user or device, how do you get permission? Some scenarios, like public safety, might operate under a legal basis, but for commercial uses, the lines are blurry. There's also a significant risk of misuse. This technology could, in the wrong hands, be used for pervasive surveillance, tracking people's movements, or building detailed profiles of their behavior without their knowledge. Building public trust will require complete transparency from network operators about what sensing is happening and what rights individuals have. And, of course, we need to secure this new data. If sensing data can be hacked, spoofed, or manipulated, it could be used to cause accidents or create chaos. Beyond privacy, there are still plenty of technical challenges to solve. ISAC works best with a clear line of sight, which is hard to guarantee in cluttered urban environments or indoors. Reflections and interference from buildings, trees, and other moving objects can create clutter that confuses the sensing algorithms. Differentiating a real target from this noise is a complex signal processing problem. Upgrading the hardware in base stations will also come at a cost, and getting everyone, manufacturers, operators, and regulators across the world to agree on standards and rules is a massive undertaking. Finally, for real-time applications like vehicle safety, the network needs to process this sensing data with extremely low latency, which will require powerful computing at the edge of the network. So, when can we expect to see ISAC in the real world? Experts believe that basic sensing features will start appearing in 5G advanced networks, with more sophisticated capabilities being standardized as part of 6G, likely from 3GPP's release 21 onwards. Early deployments will probably be in controlled environments, like private networks in factories or warehouses. We'll also see pilot projects for specific use cases, like drone monitoring or vehicle-to-network communication, in markets that are leading the 5G rollout. So, why does ISAC matter in the big picture? First, it's about efficiency. By reusing infrastructure that we've already built, we can add sensing capabilities at a much lower cost than building a whole new radar network. Second, it unlocks entirely new services and business models. Imagine sensing as a service, where companies can pay to get real-time data about foot traffic, vehicle flow, or warehouse activity. And most importantly, it's about safety and automation. ISAC can provide a new layer of awareness for autonomous systems, making our roads, skies, and workplaces safer. It's a key enabling technology for the future of smart cities, industrial robotics, and immersive digital worlds. ISAC is one of those foundational shifts that could quietly reshape what we expect from our networks. They are evolving from simply connecting our devices to actively perceiving and understanding the world around them. We're still in the early days, but the direction is clear. Telecommunications is becoming sensory. Thanks for watching. If you found this video interesting, please give it a thumbs up and subscribe for more deep dives into the future of technology. Let me know in the comments what you think is the most exciting or concerning application of ISAC. See you in the next one.